Hi all. In last video, we saw that what is the application of the Gauss law. One of the application we saw is how we can apply the Gauss law for point charges. So in this class, we will see other application, how we can apply Gauss law for line charges. So before going to the application of Gauss law, I'll go through what is general step we can follow while deriving equation for Gauss law. So first step we will take what is a D. We will identify what is D and what is the direction of D. So first step is to identify D and its direction. Second step is identify what is the surface area, that is elemental surface area ds, and its direction. And third step we have to obtain d dot ds, because Gauss law says q is equal to surface integration of d dot ds. To obtain q, we need to know what is d dot ds. So obtain dot product between d and ds. Next step, integrate that integrate that surface integral over a Gaussian surface and keep d as unknown and write the equation of d in terms of q. Next, obtain what is the charge q enclosed by that surface. So next step is to obtain the charge enclosed by that surface. And next step is determine d by equating the equation obtained in the integration of all the Gaussian surface and the equation obtained by the charge, and determine d. So once you determine d, you can obtain equation for electric field intensity by using relation between E and D, that is E is equal to d by epsilon naught. So using this relation you can obtain expression for E. So these are the general steps we can follow for every derivation. First we will identify d and its direction. Next we will identify ds and its direction. And third point is we have to find what is d dot ds, then integrate over a Gaussian surface, then equate with the charge equation and find equation for d. So once you get the equation for d, using the relation between d and d, obtain equation for E. So these are the general steps we will follow. So in next we will see what is the other application of the Gauss law. We will see in this video one more application, that is the how we can apply Gauss law for a point charge. Consider a line charge of infinite length which is placed along z axis. The one terminal of line charge at plus infinity and other terminal of line charge at minus infinity. Now I am considering this line charge has a charge density of rho l. This line charge has a charge density of rho l, which is placed along z axis. Remember, which is placed along z axis. And I am considering a Gaussian surface around that line charge. Around this line charge, I am considering a Gaussian surface, a cylindrical surface. Gaussian surface is a cylindrical surface which has a length of L and radius of R. The cylindrical surface has a length of L and radius of R. Now, what is the first step to apply Gauss law for any surface, the line charge or point charge? First step, we have to identify what is D and what is the direction of D. Now, I am considering, as for first step, I am considering the D acts along the R axis. D acts along R axis. So D is in the direction of R. So the unit vector corresponding to D is A R cap. The unit vector corresponding to D is A R cap. Now, similarly, the surface I am considering is ds, which is placed here, which is normal to R axis, because D is along D axis. So ds should be considered as in perpendicular to D. So ds is normal to R axis. The unit vector normal to ds is A R cap. Now according to Gauss law, we know that q is equal to surface integration of d dot ds. But in the cylinder, it has a three parts. One is along the sides of the cylinder, other one is along the top surface, and other one is bottom surface. So we can divide this equation, the charge in bottom surface, in top surface and side surface. So we can write this equation into three parts. One is with respect to sides, other one is with respect to bottom surface, and other one is with respect to top surface. Like this. So this part shows with respect to side surface, this part shows with respect to top surface, and this part is shows with respect to bottom surface. Now I told that the dr acts along radius, so it will have only radial component. So dr, so I can write d is equal to dr into ar cap. Similarly, ds is normal to r axis, so I can write ds in the cylindrical coordinate system. I can write r into d phi into dz, and the normal vector with respect to ds is ar cap. Now we got d, we got ds. Now obtain dot product between d dot ds, that is third step. So d dot ds, if you take dot product, it will be d dot ds is equal to dr into ar cap dot r into d phi into dz into ar cap. If you simplify this, you will get dr r into d phi dz, because ar cap dot ar cap will be equal to 1. So dr, you will get only dr r d phi dz, only scalar component you will get. Now once you get the d dot ds, so there will be three parts. One is with respect to sides, other one is with respect to top, and other one is with respect to bottom. Now if you see the diagram, top surface, the normal vector with respect to top surface is az cap, and normal vector with respect to bottom surface is also az cap. We know in previous classes we saw that whatever the component with respect, if the line charge lies along z-axis, so whatever component with respect to z-axis will be 0, because it will have same as positive component and same negative component, so it will get cancelled each other. So the whatever component produced with respect to z-axis, d component produced with respect to z-axis will be 0. So we can consider the top and bottom surface will produce 0 effect. So I can write these two products equate to 0. So d dot ds with respect to top and d dot ds with respect to bottom are equated to 0. And so now I have only one component with respect to side, so q can be written as d dot ds with respect to side surface, and those d dot ds, we know what is d dot ds, so substitute that dr into r d phi dz. And what is the limit of this integration? It has two parts. One is with respect to phi, other one is with respect to z. Now integrating this over a limit, so what is the limit? We know that what is the limit? The z-axis is varying with respect to length of the cylinder. So what is the length of the cylinder? It is L. So limit for z is 0 to L. Similarly phi is varying from where to where? It is varying from, if you start from here, it varies from 0 to it will vary from like this. If you come here again, it will be 2 pi. So phi is varying from 0 to 2 pi. So limits of the integration will be 0 to L and 0 to 2 pi. So if you integrate this, and you will get q equal to r into dr into 2 pi L. So q is equal to 2 pi r dr L. So if you rearrange and write in terms of dr, then dr is equal to q by 2 pi r L. Now, so what is this q by L? So q by L is a charge density, that is rho L. The q by L is a charge density in a line charge, so it is a rho L. So I can write rho L is equal to q by L coulomb per meter. So substituting instead of q by L, substitute rho L. So I can get equation for dr as d as q by rho L by 2 pi r into ar cap coulomb per meter square. So this is the equation for d. Now we can obtain equation for E as rho L. So equation for E, which is equal to d by epsilon naught. I can write E is equal to d by epsilon naught. So substituting d as rho L by 2 pi r into ar cap. So I can write equation for E as rho L by 2 pi epsilon naught R into AR cap. So these are the equation for D and E. So we obtained equation for D and E in a line charge. So in next video we will see what is the equation, what is the other application of Gauss law. In next video we will see the application of the Gauss law in a coaxial cable, and if coaxial cable and a spherical rings, in a coaxial cable and a spherical rings. What is the equation for D and E in coaxial cable and spherical rings? Thank you.